So, good afternoon. Today, nobody has joined this session yet, but I think we should start. So, let me just share my screen first. So, let me just give the intro. So, good afternoon, everyone. My name is Musab Rafiq. I'm a course TA for the course Digital Electronic Circuits that is taught by Professor Gautam Shah from IIT Kharagpur. I'm a PhD student at Department of Electrical Engineering at IIT Kanpur. So, today we'll be discussing problems related to week 8 tutorials. So, this is the week 8, this is the live session 8 of this course Digital Electronic Circuits. There are going to be 12 sessions. So today is the 8th session. So today we will be discussing, as already mentioned, problems related to week 8 tutorial. So week 8 will have registers, shift register, universal registers, application of shift register, ring counter, Johnson counter, sequence generator and detector, serial ladder multiplication and all. So as there are no audience members, so I'll just keep usually with audience members in the Google Meet. I get a feedback how I'm going whether I'm going fast or slow, or should I repeat any particular step. So right now there are no audience member in the meet. So what I will do, I will just explain every possible steps in the questions. So for the students who are going to watch the recordings, they will understand better. So and with the recording, you guys are at liberty, you can move forward. But I guess someone has joined the session. Let me just admit. So let me just give the introduction again. As I already said, today we'll be going to discuss problems related to week 8 material. I'm your course TA Musab Rafiq, and the course is taught by Professor Gautam Shah from IIT Kharagpur. Today we'll be discussing problems related to register, shift register, universal register and all. So all those participants who will join, it's a request, when I'm solving a particular problem, I won't be able to admit them. After a particular problem is solved, they will be admitted. And also, if you have any doubts and queries, you can use the chat box or mic, whatever will be feasible for you. So without wasting any time, let me just start with the first question. So the first question states, in the following circuit diagram, one XNOR gate with control input as 0 is inserted between the serial in serial output and serial in parallel output registers. So we have this following circuit diagram. Here we have the serial in serial output register, and here we have this serial in parallel output register, and in between them we have an XOR gate which has a control input given as 0. How many clock pulses are needed for the receiver? So receiver is here. After parallel in serial output register, so this register is parallel in serial output register to collect the bits so that the sequence 1010 is formed. So at input we give this sequence, and at receiver we want to collect the sequence 1010. So the question asks us, after how many clock pulses we will get this sequence. So here we have this serial in serial output register. Here we have serial in parallel output register. Here we have parallel in serial output register, and here we have the receiver where we are collecting the information. So what we'll do, we'll just create a table. First we'll have this clock, just a second, yeah. We'll have this clock cycle to mark the clock cycle. Then we have serial in serial output register. Then we have serial in parallel output register. Then we have parallel in serial output register. Finally we will have the receiver. So I'll just mark with X. So in the clock cycle first, this 0 will go in the serial in serial output register, and all other are. And similarly for this, and similarly for this. Then in the second clock cycle, another bit goes into the serial in output register, so it will be 1 0, and this thing will remain like this, it will remain like this will remain like this, and this will remain like this. Then in the third clock cycle we have 0 1 0, it will go like this, it will go like this, and then finally we have 1 0 1 0, it will go like this, it will go like this, it will go like this. Now for the fifth clock cycle, this 0 is here, right? And also the control bit is 0. So this is an XNOR gate, and when both the inputs are same, we know that the output of the XNOR gate is high, so that is 1. So we'll just write 1, and this is shifted here, and 0 will come here, so it will be 0 1 0 1, and this will be like this only, and this will be like this will be like this. Now sixth clock cycle, we will have 1 here, this 1 here, and 0 here, so it will be 0, so it will be 0 1, this thing, and it will be 1 0 1 0. Now interesting to note that this will toggle between 1 0 1 0 and 0 1 0 1, and this is like this, and this is like this. So then we have the 7th clock cycle, it will be 0 1 0 1. Now we have 0 here, so it will be 1, because XNOR operation of 0 and 0 is 1, so it will be 1 0 1. And for the 8th clock cycle, it will be 1 0 1 0, it will be 0 1 0 1 similarly. And also once these inputs go to here, so it will be parallel output, so we'll have a parallel output here also, so it will be like here, it will be 1, it will be 0 1, no, here in the next clock cycle, not here it will be 1, here it will be 0 1, here it will be 1 0 1, and in this clock cycle, that is 9th, 0 1 0 1, 1 0 1 0, it will be 0 1 0 1, and this, it is going to parallel in serial output. Now with serially in the from the next clock cycle, that is from the 10th clock cycle, it will be start giving this output. So I'll write this 10th here, I think I should write it here, clock cycle 9th, sorry 10th, clock cycle 10th, this is CISO, this is CIPO, this is PISO, and this is my receiver. So on my 10th, so it will be 1 0 1 0, this will be 0 1 0 1, and this will be 1 0 1 0, and this 1 will be at the receiver. Similarly for the 11th, it will be 0 1 0 1, this will be 1 0 1 0, this will be 0 1 0 1, and this will be 0, receiver will get 0. And similarly for 12th, it will be 1 0 1 0, it will be 0 1 0 1, this will be 1 0 1 0, and this will be 1. For 13th, it will be 0 1 0 1, 1 0 1 0, 0 1 0 1, 0. And finally we have this 14th, 1 0 1 0, this will be 0 1 0 1, this will be 1 0 1 0, and this 1 will come here. So at output we are having this sequence 1 0 1 0 as required. So after 14 cycles we'll be having this thing. So option C is the right answer. So how I'm able to write these things quickly now, because once I got these sequence, they will just change between these two states only, 1 0 1 0 and 0 1 0 1, and the last bit of the previous cycle here will be the received bit here. So here it was 0, here it was 1, here it was 0, it was 1, and finally when I got the sequence, I can just mark the answer as 14 clock cycles. So after 14 clock cycles, I'm able to get the sequence 1 0 1 0. So any doubts? If not, we can move forward to question number 2. question number 2 states that which of these LFSR, so LFSR is linear feedback shift registers, circuit 1 and circuit 2 can generate maximum length sequences. So we know that the circuits which generate the primitive polynomials can generate a maximum length sequences. So a primitive polynomial is the one which generates a maximum length sequence. And we know for these we are having 4 flip-flops in both of these LFSR. So we know that for n equal to 4, the primitive polynomial is given as x raised power n plus x plus 1. And also we know that if the circuit is tapped at n, m and l and it generates a primitive polynomial, so I'll just write here, if it generates a primitive polynomial, then the circuit where the tapping is done at n minus n, n minus m and n minus l will also generate a primitive polynomial. So now looking at the circuit 1 and circuit 2, let's just take for circuit 2 first. The tapping is done at, so here it is x raised power 0, this is x raised power 1, for brevity I'm writing here x raised power 2, x raised power 3 and x raised power 4. Similarly here x raised power 4, x raised power 3, x raised power 2, x raised power 1 and x raised power 0. So looking at this circuit, so it will generate the output f of x as x raised power 4 plus x raised power 0, that is 1. So this is a primitive polynomial. And also we can write x raised power 4 minus 4 plus x raised power 4 minus 1 plus x raised power 4 minus 0 will also be a primitive polynomial. So that means x raised power 4 plus x raised power 3 plus x raised power 0, that is 1, will also be a primitive polynomial. Now this was circuit 2 and now we have circuit 1. So circuit 1, the tapping is at x raised power 4 and x raised power 3, and so it is x raised power 4 plus x raised power 3 plus x raised power 1. So this is equal to this, and which means it's also a primitive polynomial. So both of these circuits are primitive polynomial. That means both of them can generate maximum length sequences. As both of them can generate maximum length sequences, so we'll mark option D as the correct answer. So I'll just repeat here. So we know that for n equal to 4, the primitive polynomial is of the form x raised power n plus x plus 1. And also if the tapping is done at the points n, l, m, n, then n minus n, n minus m and n minus l are also primitive polynomials. You know that primitive polynomials, there are two necessary conditions, that the number of tapping should be even and the tapping should be co-prime, like here 4 and 3 and 4 and 1. So for circuit 2, my primitive polynomial that it generates is f of x is called x raised power 4 plus x plus 1. So this is a primitive polynomial, and using this property we can also say that x raised power 4 plus x raised power 3 plus 1 is also a primitive polynomial. And this primitive polynomial is generated by circuit 1, by where the tapping is at x raised power 4 and x raised power 3. So for circuit 1, f of x was equal to x raised power 4 plus x raised power 3 plus x raised power 4 plus 1, and both of them generate primitive polynomials, and as a result both of the options are correct. So option D is the right answer. So any doubts? If not, then I think we can move forward to question number, this was 2, now 3. Let me just insert the video first. So question number 3 states, in the following diagram, register A and B were loaded with 0, 0, 0, 1, 0, 0, 1 and 1, 0, 0, 1, 0, 0, 0, 1 respectively. So register A, which was this register, was loaded with 0001001, and register B was loaded with 10010001. The flip-flop out was initially reset, so the flip-flop here is a T flip-flop. It was initially reset, so the output was 0. After 8th clock pulse, what will be the loaded sequence in the register A? So the question asked that it has given the conditions on register A and B where the bits were loaded, and also the output was reset. That means Q was equal to 0 for a T flip-flop. Now after 8th clock pulse, what will be the loaded sequence of register A? So let's just first examine the circuit. What is happening there? We have this register A and we have this register B. So serial in, serial output register, serial in, serial output register. So it is an 8-bit register, 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8, and its output, serial output, goes to the full adder as AI, and from register B another input goes to the this full adder as BI. Now the full adder's output goes to the serial input of register A, and register B is as it is. The contents of the register B don't get updated, they remain as it is. And we have this carry. This carry goes to the T flip-flop as an input to the T flip-flop, and this input carry, that is Ci-1, is the output of the T flip-flop. So we have this AI, we have this BI, we have this Ci-1, then we have this Si, that is going to serial input of register A, then we have this Ci, that is the carry output of the full adder, that is going to the input of the T flip-flop, and the output of the T flip-flop Q is going to the input of the input as an input carry to the full adder. So let's just fill up the register A and B with the contents. So this is 0 0 0 0 1 0 0 1, and this is 1 0 0 1 0 0 0 1, right? And this is initially 0. So let me just mark it here, let me just shift it. Yeah, so this is clock, this is AI. So what will be AI? AI will be this bit. So after shifting, whatever will be the present here will be my AI as it is going to the full adder. BI similarly for this serial in, serial output register, once the contents are here, that content will be my BI, that bit. Then we have Q, then we have S, then we have CI, and finally we have the contents of register A. So initially, let's just mark the initial condition for clock cycle 0, that is serial clock equal to 0. My AI is 1, my BI is 1, and as given in the question, someone has joined the session. Let me just admit the person first. So as new participant has joined the session, let me just quickly repeat the question. So we have this question: in the following diagram, register A and B were loaded with 00010001 and 10001 respectively. So I have just loaded them these, and the flip-flop was initially reset. This T flip-flop was initially reset, that means Q equal to 0. And after the 8th clock pulse, what will be the loaded sequence in register A? So here we have this full adder. So AI is coming out to be from the serial output of register A, BI is the serial output of the register B, and Ci-1 is the output of the T flip-flop, and then the sum goes back to the serial input of register A, and the carry goes to the input to the T flip-flop. Now we need to find out the output after the 8 clock cycles. What will be the loaded sequence in register A after 8 clock cycles? So initially we'll mark it as clock 0. So my AI will be 1, my BI will be 1, my Q will be 0 as given in the question, my SI will be 0, and my sum will be SI will be 0 because 1 plus 1 is, just a second. So my sum will be 0 because 1 plus 1 is 0 and carry is 1, and Ci will be 1, and my register contents will be 0 0 0 0 1 0 0 1. This was the initial condition. In the next clock cycle, my AI will be 0, my BI will be 0 because this shifting takes place. My AI will be 0, my BI will be 0, as CI is 1. So CI means 1 means T equal to 1, and when T equal to 1, toggling happens. So if Qn minus 1 was 0, Qn will be 1. If Qn minus 1 was 1, Qn will be 0. So Q was 0, so Q will become 1, and my sum will be 0 plus 0, and my Ci minus 1 was also 0. This Ci minus 1 was 1. Yeah, Ci minus 1 was 1. So my sum will be equal to 1, and my Ci will be equal to 0, and my contents of the register will be coming from this. So it will be 0 0 0 0 0 1 0 0. This 1 was shifted, and this 0 was updated. This 0 was updated, and this 1 was shifted. Now clock cycle 2, my AI will be 0 and my BI will be 0. Ci is 0, that means Q will remain as 1. Sum will be equal to 1. Sum will be equal to 1 because my Ci minus 1 is 1. And my carry will be 0. So this 0 will be here. So 1, 2, 3, 4, 5, 6, and then 1, 0, right? Now over to the clock cycle 3. Oh, it will be 1 1 because s equal to 1. Yeah, sorry, it will be 1. Now over to clock cycle 3. My AI is again, so 1 1 is done, 0 1 0 0 is done, this is done, this is done, this is done. My AI will be equal to 1, and my BI will be equal to 0, and my Q will be equal to 1 again because no toggling happens, as Ci is equal to 0, and my S will be then equal to, because Ci minus 1 was 1, so it will be 1 plus 1, that is 0, and carry will be 1. This 1 will come here, so it will be 1 1, then 5 zeros, 4 5, and then 1. Now fourth clock cycle, my AI will be, this is done, my AI will be 0 and my BI will be 1 0 1. Q, since Ci is equal to 1, toggling will happen, so this will become 0, and my sum will be equal to 0 plus 1 plus 1, so that is 1 0, so 1 and 0, so it will be 0 1 1 0 0 0 0 0. So similarly we can fill up the contents. So I'll just show for quickly, I'll show for 5 and 6 and 7, then I'll show this 8th one. So it will be 0 0 0 0 0, it will be 1 0 1 1, 4 zeros. Then the 6th clock cycle will again be equal to 0 0 0 0 and 0, so it will be 0 1 0 1 1 0 0 0, and for the 7th clock cycle it will be 0 1 0 1 0, and this will be equal to 0 0 1 0 1 1 0 0. And in the 8th clock cycle there are no contents in the B register, and this register will get updated with this value finally, this value, sorry. So it will be 1 0 0 1 0 1 1 0. So 1 0 0 1 1 1 1 0 0 1 1 1 0 is the right answer. So 1 0 0 1 0 1 0 0 0 1 1 0 is the right answer. So option B is the correct answer. After 8 clock cycles, the contents of the register will be 1 0 0 1 0 1 1 0. So that will be my answer. Any doubts in here? If not, I think we can move forward to question number 4. So the question number 4 asks us, suppose you are designing a register IC with strictly predefined chip area and fabrication technology. So the area technology and fabrication technology is predefined. You are given a choice to either implement a serial in serial output or parallel in parallel output register. Let the serial in serial output register and the parallel in parallel output IC contain maximum of X and Y number of bits at a time respectively. So we need to choose the probable relation between X and Y. So X and Y represent the number of bits at a time. So we know that the number in parallel output register, it will incorporate lesser number of flip-flop. So this thing will incorporate lesser number of flip-flops. Why it will incorporate lesser number of flip-flops? Because in parallel output, it has more input and output pins. So for the incorporation more input and output pins, so it will require lesser number of flip-flops as compared to the serial in serial output, and as a result, if it incorporates lesser number of flip-flop, it will have lesser number of bits at a time. That means Y will be less than X, and as a result, that means the number of bits in serial in serial output at a given time will be greater than the number of bits in parallel output. So for option D, X greater than Y. Now question number 5, this asks us, in the following circuit diagram, so we are given this circuit diagram, the desired frequency of the output signal is 10 kHz. So output frequency, let's just say it F out, is 10 kHz. This is the desired. How many number of inverters? So how many number of inverters? So it's asking us how many numbers, approximate inverters M, are to be cascaded to achieve the desired specifications. So here we will have the cascade of inverters, and we need to find out the number of inverters, that is M, required to achieve the desired frequency, output frequency. And also it is given as the propagation delay of individual inverter of each inverter is 5 nanoseconds. So let's just mark the propagation delay, TP is equal to 5 nanoseconds. So before going to this cascade part, let's just look at this part. Let me just use a different color. This part, if we carefully examine this, what is this? It consists of two flip-flops, and the output of the second flip-flop is connected to the input of the first flip-flop, and we know this topology, this refers to twisted ring counter or Johnson counter. So this is twisted ring counter of two flip-flops. That means it will count 2 into 2, 4 states. And we know that the output of twisted ring counter or Johnson counter is equal to input clock frequency divided by 4, right? And that implies F output, that is the required frequency, is equal to F input by 4. Now we need to figure out what this F input is equal to. So now just consider this block, the cascade of inverters block, and we know when M inverters are cascaded, the frequency that they will show is 1 by 2 into M into the propagation delay, where m is the number of inverters in the cascade and Tp is their individual propagation delay. And this will be equal to 1 by 2 into m. We need to find out that Tp is 5 nanoseconds, so 5 into 10 to the power minus 9, as we are working in SI units. Now plugging this value of this F input here, we'll get F out is equal to F in by 4, that is equal to F in is equal to 1 by 4 multiplied by 1 by 2 into m into 5 into 10 to the power minus 9, and this thing is equal to 10 kilohertz, so that is 10 into 10 to the power 3 is equal to 1 by 4 times this thing. Now that implies m is equal to 1 by 4 into 2 into 10 into 10 to the power 3 into 5 into 10 to the power minus 9. So that implies this thing is equal to 5 to 10, so that is 10 to the power 5. 1 by 4 into 1 by 10 to the power minus 5, 10 to the power minus 9 minus 5, so 10 to the power minus 4. So this thing will be equal to m will be equal to 10 to the power 4 multiplied by 0.25, so that implies m equal to 2500. But m can't be an even number, as with even numbers, if even numbers of inverters are cascaded, we are not having a clock, it won't generate a clock. So we need m to be equal to odd, then only we can have the proper clock formation. And the closest number from the options to this 2500 is 2499, so we can just say that with the approximation m equal to 2499. So option C will be our correct answer. So this was question number 5. Now let's just take a break of a couple of minutes, then we can discuss question number 6. Okay, now we will discuss question number 6. So the question number 6 states that suppose a 4-bit Johnson counter is initialized with 1111. Which of the following value converted to decimal will not occur in its counting states? So we are given these three options 753, and we have this Johnson counter, 4-bit Johnson counter that is initialized 1111, and we are required to find which of the states will not occur in the counting. So the Johnson counter, as we saw earlier, also known as twisted ring counter, where the output of the last complemented output of the last flip-flop is applied as the input to the first flip-flop, and as a result it will have the states equal to 2 into the number of flip-flops, so it will have 2 n states. In ring counter we have n states, in twisted ring counter we have 2 n states. So as the Johnson counter is initialized as 1111, so it's initialized as 1111. So someone has joined in, let me just admit the person. So let me just repeat the question. Suppose a 4-bit Johnson counter is initialized with the sequence 1111. Which of the following value converted to decimal will not occur in its counting states? So the options are 7, 5 and 3. So as you saw earlier, the Johnson counter, it has cascade of these flip-flops, and the last output of the last flip-flop, the complemented output, is connected to the input of the first flip-flop. This is also known as twisted ring counter, and it will have 2 n states, counting states, where n is the number of flip-flops, n is the number of flip-flops. For a ring counter we will have n states. So here we have this twisted ring counter, it is initialized with 111. So as it is initialized with 111, my Q bar will be 0. So in the next cycle my input will be 0 to the first flip-flop. So and that will go to the next cycles, and so on. So the twisted ring counter, initially it was 1 1 1 1. In the next clock cycle it will be 0, this thing, it will come here, and all other ones will just right shift 1 1 1 1. Then again the 0, because we are taking complement, so it will be 0 0 1 1. Then it again will be equal to 0 0 0 1, and then it will be equal to 0 0 0 0. Right, now this Q is 0 and Q bar will be 1, so now Q1 will come here, so we will have 1 0 0 0. Then we will have 1 1 0 0. Then we will have, let me just mark the arrows for brevity, 1 1 1 0, and finally we'll again have this 1 1 1 1. So 1 2 3 4 5 6 7 8, and this is a repetition of the first state. So among the options, which of the following is not here? So this thing is equal to 15, this thing is equal to 7, this thing is equal to 3, this thing is equal to 1, this thing is equal to 0, this thing is equal to 4 plus 2 is 6. Yeah, this thing is equal to 6. No, 1 0 0. Sorry 1 0 0. This is equal to 8. 1 2 4 8. Yeah, this is equal to 8 plus 4 12. This is equal to 8 plus 4 plus 2 plus 14. So these are my 8 states, and among the options 5 is not present. This thing can easily be also found in Johnson counter. We have things like this 1 1 1 1 or 0 0 0 0 0, means there are two ones are together. There is no such thing as 1 0 1 or 0 1 0 if initialized with 1 1 1 or 0 0 0. So there is no such thing as 0 1 0 or 1 0 1. So that means we could have easily ruled out 5. So this was one short to answer the question, but better to use this elaborative method. Now going forward to this was question number 7. Now moving forward to this, no, this was 6. Now moving forward to question number 7. Sorry. Question number 7 states that let a binary sequence transmitter is following the CRC3 coding with the polynomial x cube plus x plus 1. The input sequence to be transmitted is 100111 with 000. Assuming internal feedback, what are the reminder check bits to be appended with the original input stream? So we need to find out the appended bits that are to be appended to the original input stream using this CRC3 coding with polynomial f of x equal to x cube plus x plus 1. So if you recall from your lectures, this CRC means cyclic redundancy check, and this thing is nothing but we are having this D flip-flop. This is termed as 1, and its output here is going to this XOR gate, which refers to the internal feedback, and this is my D2. So this is Q, this is Q2, and this is D3. This is Q. So the tapping is at x cube and x. So we have, this is my first, this is my second, and this will go here, and this is my D, this is serial in, this is my output here, and also we have clocks which I'm not showing here, but here there are clocks. So what we have Q1 D1 is equal to S in XOR with Q3. Then we have D2, so this is D1, D2, D3. D2 is equal to Q1 XOR with Q3. Then we have D3, that is equal to Q2, and we know that for a D flip-flop, Qn plus 1 is equal to Dn. Now let me just make the table. The transmitted bits here, let me just write it here, transmitted bits that are 1 0 0 0 1 1 1 2 3 4 5 6 7, and then we have the 0 0 0 which are applied at the end. Here we have clock, I'll just write CK. Here I'll just write S in. Here I'll write Q1. Here I will write Q2, and here I will write Q3. So my clock is 0. My SN will be this 1. Starting from here, it will be this 1. Q1 will be 0 0 0 in the next clock cycle. So D1, so what will D1 be equal to? S in XOR with Q3. So 1 XOR with 0 is 1, clock will be 1, so sorry 1, this is S in, so S in second will be 0. So D1 is equal to S in XOR with Q3. S in XOR with Q3 is 1 0, that is 1, and that means Q3 in next cycle will be 1. Q1 in next cycle will be equal to 1. Now for Q2 D2 will be equal to Q2 XOR with Q3. So 0 XOR with 0 is 0, so Q2 will be equal to 0, and Q3 is simply D2. So D2 in D2 was 0, so Q3 will be equal to 0. Now for clock cycle 2, so Sn is now another 0, so 1 0 0. Now D3 was equal to Sn XOR with Q3, so 0 XOR with 0 is 0, so Q1 was 0. Q2 was Q1 XOR Q2 was D2 was Q2 XOR with Q3, so that is uh, D2 was Q1 XOR with Q3, so that was 0 XOR with 1, so that is 1, and Q3 was equal to D2, so D2 was equal to 0, so it will be 0. Now for the third clock, so 1 0 0, now another 0, so this one. So D1 was equal to S in XOR with Q3, S in XOR with Q3, 0 XOR with 0 is 0. D2 was equal to Q1 XOR with Q3, so 0 XOR with 0 is again 0. And D3 was equal to Q2, Q2 was equal to 1, so it will be 1. Now clock cycle 4, we have this 1, so this will be 1. S in XOR with Q3 is 0 XOR with 1 was 1, 0 XOR with 1 was 1, and 0 was 0, so 1 1 0 for clock cycle 4. Now from here I will write continue to, I will write clock, so this is clock cycle 4, and this is Q2 1, Q2, Q3. So clock cycle 5, this is S in XOR with Q3, 1 XOR with 0 is 1, so Q1 will be 1. Q1 XOR with Q3 is again 1, and Q2 is also 1. So for 5th clock cycle, output is 1 1 1. For 6th, my SN, so SN is here, SN, so SN was 1, now it will be another 1, so SN was 1, so this one is 1 also here, so 1 XOR with 1 is 0, 1 XOR with 1 is 0, and Q2 was 1, so it will be 1. For 7 it will be 1, 1 XOR with 1 is 0, 1, 0 XOR with 1 is 1, and this will be 0. Then 8 will be 0, 9 will be 0, 10 will be 0 from these three. So 1 XOR with 0 is 1, 0 XOR with 0 is 0, and this will be 1, 1 0 1. So for 8 it will be 0 0 1, 0 0 1. Okay, 7, this was 0, okay, 7th was 0, okay, this was 0, 0, 8, 9, 10 is 1, so 0, 0, okay, this is now 8th is 0 1 0 1, now 9th will be 0 XOR with 1 is 1, 0 XOR with 1 is 1, 1 XOR with 1 is 0, and this will be 0, and now for the 10th, that is the final, so this will 0 XOR with 0 is 0, 1 XOR with 0 is 1, and this will be 1, so this was 1 here. It was 0 0 1, 0 0 1 0. So finally the remainder will be 0 1 1 1. So the remainder check bits are 0 1 1. So option A. So what we do here, so essentially what we do here is, so this is my this state. So what we do is this Sn I have to XOR with S3, Q3, and then I write this output here. And also I do Q1 XOR with Q3, I write that output here, and Q2 is here. So see, Q2 is simply here. Here these are the results of the XOR operations, and here are the input bits that are to be transmitted. So finally we got the remainder equal to 0 1 1. So 0 1 1 need to be appended to the original bit string. Now this was question number 7. Now moving forward to question number 8. This is a true false question. which of the following statements is or true? So option 1 is universal shift register can have 4 configuration SISO, SIPO, PIPO, and PIP, so with either left or right shift. A universal shift register is a bidirectional shift register with any of the 4 configurations. IC 7495A is not a built-in shift register. IC 7595A has both built-in right and left functions. So you might have gone through the lectures and people will be knowing the answer. So option 3, that is IC 7495A, is not a built-in universal register. Universal shift register is the only correct option here. all other statements are false, so option 3 is the only true statements, and corresponding to that option C is the right answer. So option C is the right answer to this question. Now moving towards question number 9. Question number 9 asks us, suppose an 8-bit Johnson counter is initialized with the sequence 0, 0, 0s and zeros. In the decimal representation, what is the mean value of its counting state sequences? So we need to find out the sequences, we need to find out the counting states, and then finally we need to find their mean. So Johnson counter, which is also known as two-stepping counter, is already mentioned. If it's an n-bit Johnson counter, it consists of n flip-flops and it will count 16 states, that is 2n. So our first state is 0, 0. Let me just separate them. This is Q1, Q2, so on up to Q8. This is the decimal value here. So decimal value of this thing is 0. Now we'll have 1 here, and this will, all other bits will be shifted towards the right. So 1, 0, 0. So this will be equal to 1, 2, 4, 8, 16, 32, 64, 128. This will be equal to 128. Then we have 1, 1, then all are zeros. So this is 128 plus 64, and that is 128 plus 64, that is 192. That is 192. Then we have 1, 1, 1, 0, 0, 0, 0, 0. So that is 192 plus 32. So this is 4. This is 192 plus 32. So this is 2. And this is 1 carry. So 2, 2, 4. Then we will have 1, 1, 1, 1, 0, 0, 0, 0. So that is 2 to 4 plus 16. So that is 6 plus 4 is 0. This is 1 plus 2, 3, 2 plus 1, 4. This is 240. Then we have 240 plus 8, that is 2, sorry, that is 248. Then we have 0, 0, 248 plus 4, that is 252. Then we have 1, 1, 1, 1, 1, 1, 0, that is 254. And finally we have 1, 1, 1, 1, 1, 1, 1, that is 255. Now 0 will propagate, so it will be 0, 1, 1, 1, 1, 1, 1, 1. So it will be 128 minus 1, that is 127. Then it will be 0, 0, 1, 1, 1, 1, 1, 1. So it is 64 minus 1, that is 63. Similarly, moving forward, so it will be 0, 0, 0, 1, 1, 1, 1, 1. 32 minus 1, that is 31. Then it's 0, 0, 0, 0, 1, 1, 1, 1. This is simply 15. Then we have 0, 0, 0, 0, 0, 1, 1, 1. That is 8 minus 1, that is 7. 0, 0, 0, 0, 0, 1, 1. 4 minus 1, 3. And finally we will have 1. And then we have 0, which we won't write here because we have already started with 0. So our mean will be equal to 0 plus 128 plus 192 plus 224 plus 240 plus 248 plus 252 plus 254 plus 255 plus 127 plus 63 plus 31 plus 15 plus 7 plus 3 plus 1, and this thing is divided by 16 to get the mean. So let me do the addition. So it is 128 plus 192 plus 224 plus 240 plus 248 plus 252 plus 254 plus 255 plus 1 plus 7 plus 31 plus 15 plus 7 3 plus 1 divided by 16. So it is 2040 divided by 16, and that is equal to 127.5. So option C is my correct answer. So this was question number 9 of today's live session. Now I think we can discuss question number 10. If there are any doubts, please type in. So now let's just discuss question number 10. In the following circuit diagram, both register X and Y is loaded with binary sequence 1101. So register X and Y are loaded with 1101. What is the binary sequence in register M after the 4th clock pulse? So this is a we have this register and we have this shift register here. From the lectures there is this difference. The shifting happens here like this, not like this. So that is one key difference here. Shifting happens like this. We have this M where this AND product goes directly to M0, and for the M register from bits M1 to M7 go to the full bit adder as A7 to A1, and these go as 1 2 3 go as B this 1 to B is 1 2 3, and the all other 4 bits are 0 0 0. So just like in the lectures, I will just have this. I will construct the same table. Here we'll have this clock, right? So we have 4 clock cycles, so 1, and here I will have this X, here I will have YI. So Y, let me just write here is 1101. So first this 1 will go here, and this is 1101 as it is. This is 1101. This YI, this bit Y0 bit is here as 1. Their AND operation I'll write here, that is equal to 1101, because 1101 ANDed with 1 is 1101 itself. Then we have the M output from the last clock. So here it was initialized with 0 0 0. So 0 0 0 0 0 0 0 1 2 3 4 5 6 7 8 1 2 3 4 1 2 3 4 5 7 8. Here I will have the M that is input to the adder, and here I will have the other input that is input to the adder, and finally, so let me just we have space issues, let me just use a new slide here. So I'll just push it slightly upwards so we don't have any space crunch. So here I will write clock, here I will write X, here I will write YI. So these two can fit in small width. Then I have M from previous, so I will write it previous. Then I have M that is input to the adder MI. Then I will have another input that will I will write OI, and then I will have the M. So this thing, and this thing. So this is clock cycle 1, this is clock cycle 2, this is clock cycle 3, and finally we have the fourth. So here this is clock cycle first, X is 1101, Y is 1, 1101, so this 1 will go here, and their AND, I haven't written their AND, one column I forgot, so let me just write here, and is equal to 1101. So my contents of the M register after the previous cycle are 0 0 0 0 0 0 0. So this is my M7 and this is my M0. M7 doesn't go to the full adder, only the contents from M0 to M6 go to the full adder. So Mi, which is the input to the next adder, is 0 0 0 0 0 0 and 0 1 2 3 4 5 6 7, and also I will write here another 0, that is not an input to the next adder, but for the addition purpose I will write here, that is 0. And my another input that goes to the adder is AND, that is these 3 bits, that is 1 1 0 and 4 are zeros from here, and I will write 1 here, this one. Input to the adder are only marked with red, keep that in mind. This black doesn't go to the adder. You can also refer to your lectures where they have marked the input to the adder as blue and the one that is not going to the adder as black, so I will just use the same color coding scheme. And finally we have the adder output. So this will be 1 simply, this is 0 1 1 0 0 0 and 0, right? In the next clock cycle my input is again X equal to 1 and my Y is 0, so AND will be equal to 0 0 0 0. Now the previous M of previous is equal to 0 0 0 0 1 1 0 1, and other input is equal to 3 zeros coming from the 3 AND operations and 4 zeros. No, first I'll write this, let's write this. So 0 0 0 1 1 1 1 0, this is not here, and here I'll mark it with 0, and the other input will be equal to these 3 zeros and those 4 zeros, and my output will be equal to the addition of them. So it is 0 1 0 1 1 and then zeros. Now the third clock cycle my input is 1 1 0 1, Y is 1, so their AND will be equal to 1 1 0 1. My MI from the previous clock is 0 0 0 1 1 0 1 0, and my input to the adder will be 0 0 1 1 0 1 0 1 2 3 4 5 6 7 3 4 5 6 7, and that M7 will not be an input to that. I will write here 0, and the AND operation I will write down the 1 here, it will not go to the input to the adder, and other will go, so this is 0 1 1 then 4 zeros, and their addition. So it is 1 0 0 0 0. Oh. So that thing is 1 and 1. Now the fourth clock cycle. Here I have input 1 1 0 1 and my y is 1. Their AND will be equal to 1 1 0 1. Output from the previous cycle is 1 0. Output from the previous cycle is 0 1. It's not here. 0 1 0 0 0 0 1 0. And the input will be 1 0 0 0 0 0 1, and this will be not be an input to the adder. This will be here, and my next output will be 1. So it will be 0 1 1 and 4 zeros, and this will be my final answer. So this will be 1 1 1 1 0 0 0 1. So after 4 clock cycles, my output will be 1 0 0 1 0 0 0 1 1 1 1 1 0 0 0 1 1 1 1. So option D is my correct answer. Now moving forward to question number 11. So question number 11 asks us, the group of bits 0 1 1 0 is serially shifted. So 0 1 1 0 0 is serially shifted. Write mode bits first. So write mode bits first into a 5 bits parallel output shift register with an initial state 0 1 0 1 0 1. What is the value of the contained register after 2 clock cycles? So this is the serial in-scene output register, and it goes to parallel output register. So at clock equal to 0, my present state of which one? Parallel output register, this one, is given as 0 1 0 1 1. After first clock cycle, the write bit first is going to the parallel output register, and as a result it will be this 0 will come here, so it will be 0, and this will write shift, so it will be 0 0 1 0 1. And after second clock cycle, again this second 0 will come, so it will be 0 0 0, and the right shifting will occur, so it will be 1 0. So after 2 clock cycles, my contents of the register will be 0 0 0 1 0. So see, initially it was 0 1 0 1 1. This register output from the serially shifted register goes into this, and this 0 comes here, and this changes to, and this right shifting occurs, and it will be 0 0 1 0 1, and then the other 0 comes, and it will be 0 0 1 0. So 0 0 1 0 will be my correct answer. Now let's just take a break of a couple of minutes, so those guys who are watching recordings, they can seek by 2 minutes forward. They can seek time by 2 minutes forward. They can skip to after 2 minutes, and since no one is in recording, so let's just take a break of 2 minutes. So let's resume. Now question 12 is a theoretical question. It asks us if the register have both shifts and parallel load capabilities, they are referred as. So the register which has both parallel and shift load capabilities, they are referred to as universal shift registers. So you must be knowing that. So let me just quickly skip to the next question. Question number 13. The initial content of 4-bit serial in parallel output register is shown in the figure. It's 1100, so it's given as 1100. After 4 clock pulses are applied, the content of the shift register will be. So we need to figure out the contents of the shift register after 4 clock pulses are applied. So we have this serial in parallel output register, and we need to figure out the contents of the register after 4 clock pulses are applied. So what happens here is these two outputs get XNORed and they are applied to the input here, and here we have the clock. So we'll write here clock 0, and this is the present state. So when clock was initially 0, so initially the contents of the register were 1100. In the next clock cycle, what happens? These two are XNOR bits, so this is 00, so 0 XNOR and 0, their XNOR output is equal to 1. So 1 will go as a serial input, and there will be this will shift to here, this will shift to here, and this will shift to here, and this thing will come here. So 00, its output is 1, and these two ones will shift, and the 0 will also write shift. Now after the second clock pulse, so we have 10, 10. So we know that XNOR of 1 and 0 is 0, because XNOR is this output of XNOR is only high when both of the inputs are same. So let me just write XNOR 0, 0, 1, 1, output is 1, 0, 1, 1, 0, output is 0. So here 1, 0 is the input, so my output will be equal to 0, and that will go here. So this one will shift here, this will shift here, this will shift here. So here it was 1, so shifting will occur. So here will 0, 1, 1, 1. After third cycle, what we have is 1 and 1. So again it will be 1 and 1 will be 1. So it will be 1, 0, 1, 1. And the fourth clock cycle, it is again 1, 1. So it will be 1, 1, 0, 1. So after 4 clock cycles, my state of the register is 1, 1, 0, 1. So option 2 is the right answer. So since no one is in the meeting room, let me just repeat. So initially the contents of this serial in parallel output register were given as 1100, and my third and fourth output are XNORed and given back as a serial input. So we need to find out the contents of the register after the 4 clock pulses. So initially when clock was equal to 0, my present state was equal to 100, and this 0 and 0 are XNORed, and then it gives the output 1. So this 1 comes here, and all of the bits are right shifted, so it will be 1, 1, 1, 0. Similarly, this is 0, 1, that is 0, so right shift all other bits 1, 1, 1. So it is 1, 1, right shift these bits. So it's 1, 1, that is 1, and right shift these bits. So after 4 clock pulses, my state of the register is 1, 1, 0, 1. So option 2 is the correct answer. So these 3, 4 questions are along the same lines. So same lines. So I have kept them so you'll get practice with these types of questions, as they are involved in other questions also. And in the next week we'll be discussing questions related to counters only, because the week 9 tutorials deals with the counters. So question 14 says as a 4-bit serial in parallel output register is initially set to 111. So we have a 4-bit serial in parallel output register that is initially set to 1111. The data 1010 is applied to the input. After 3 clock cycles, the output will be, so 1010 is applied to the input. So after 3 clock cycles, we need to figure out what are the contents of the register. So here I will have clock, here I will have the present state. So at the initially it was 1111, then I am applying data 1010. So here the 0 will come here first, so it will be 0 and 111. Then in the second clock pulse it will be this, it it will be right shifting will occur, and this 1 will come here, so it will be 1 0 1 1. So this 0 come here and this one came here. Now another 0 will come here, so it will be 0 and right shifting will happen, 1 0 1, and after 4 clock cycles this 1 will come here, so it will be 1 and the right shifting will occur, so it will be 1 0. So after 3, we need to find after 3 clock pulses. So after 4th it will be 1 0 1 0, but we need to find out after the 3, so it will be 0 1 0 1. So after 3 clock pulses, the correct answer is 0 1 0 1. This was for after 4 clock pulses, this was after 3 clock pulses, because the question was asking us 3 clock cycles. So now this was question number 14. Now we will discuss question number 15. Question number 15 asks, what is the output after 2 clock pulses for a bit sequence 1101 serially entered into a 4-bit parallel output shift register, which is initially clear? So initially I had thought that I will give this question as a assignment to the live audience, but since there are no live audience, so let me just show the solution, because it's somewhat similar to the earlier questions. That's why I had kept it here. As there are no live audience, now let me just show the solution directly. So if you are watching the recording, I just request you just do it first, then watch the solution. So what is the output after 2 clock pulses for a bit sequence 1101 serially entered into a 4-bit parallel out shift register, which is initially clear? So we have this clock and we are entering a data 1101 to a 4-bit parallel output shift register. So clock equal to 0. Initially it was all clear, so it was 0 0 0 0, and we need to find out the output after 2 clock pulses. So after first clock pulses, this 1 will go here and all other will shift, so it will be 1 0 0 0. After second it will be 0 1 0 0. After third it will be 1 0 1 0. After fourth it will be 1 1 0 1. But we need to find out the output after the second clock pulse, so it will be 0 1 0 0. So let me just repeat. What is the output after 2 clock pulses for a bit sequence 1101 serially entered into a 4-bit parallel out shift register, which is initially clear? So initially it was clear, so it was 0 0 0 1. So 1101 is added, serially added, so 1 will go here and other will right shift. Then 0 will add here and other will right shift. Then 1 will add here and other will right shift, and then again 1 will add and other will right shift. And we need to find out the contents after the second clock pulse. So that was 0 1 0 0. Now a shift register with its complement output Q0 of the last stage connected to the D input of the first stage is called. So we have a shift register where that is cascaded, and its output Q0 is connected to the input of the first stage is called, as discussed a couple of times during this live session, this is a twisted ring counter or a Johnson counter. So this is a twisted ring counter, and for a twisted ring counter, if there are n flip-flops, so the number of states it will count is 2n. And for a ring counter, in ring counter, let me show. In ring counter, this is connected. So in ring counter, only n states are there. We will see more about counters in the next lecture. We will discuss questions related to counters extensively in the next live session. Now towards the last question of the today's live session. So the following circuit is a, so let us quickly examine the circuit. The following circuit is a, so what is happening here? We have a D flip-flop whose output is connected to another D flip-flop whose output is another connected to D flip-flop, and whose output is connected to D flip-flop, and its output is connected to the first stage. And we have clock given, same clock given to the all flip-flops, and we have this preset here, and we have this clear here. So this thing is simply a ring counter. Now what will be the modulus of this ring counter? So the number of states it will count is simply equal to n, equal to number of flip-flops, so it is mod 5. So this thing is mod 5 ring counter. So option 1 is correct answer. And also one thing, if it was a Johnson counter where this thing was connected, we would have called it a mod 10 Johnson counter, because it would have counted 2n states. Because in Johnson counter, if there are n flip-flops, it will count 2n states. I'm not sure whether we'll call it as mod 10 Johnson counter or mod 5 Johnson counter, because mod 5 Johnson counter will itself mean 10 states. So that thing we need to confirm. But regarding this mod 5 ring counter, this is correct. So ring counter which has 5 flip-flops, it's referred to as mod 5 ring counter. So that was all for today's live lecture. As there are no participants in the live room, I think I can end, but let me just, since we have some time left, let me just pick a question again and let me just try to explain it again. I think question number, let me just pick one question and repeat, which I feel like needs a repetition. These last few questions were quite easy. Actually, I wanted this live audience to do them simultaneously, but unfortunately for the first time we are not having any live audience here. So yeah, let me just repeat this question. This is an interesting question. So we have this binary sequence transmitter is following a CRC, that is cycle redundancy check coding with polynomial function x cube plus x plus 1. So here we have this x cube, this is x, this is x cube, this is having internal feedback. The input sequence should be something 1 0 0 1 1 1. So input sequence is 1 0 0 1 1 1, and we have this state 0 0 0. So we need to find out the remainder check bits that are to be appended to the input stream. So here we have this clock. So this serial in transmitter will have first this 1. So this 1 is here, and all other states are 0 0 0. And we have this condition D1 is equal to S in XOR with Q3, D2 is equal to Q1 XOR with Q3, D3 is equal to Q2, and we know that Qn plus 1 is equal to Dn. So D1 will be here equal to Sn XOR with Q3, that is 1 0 is equal to 1, and that implies Q1 in next cycle will be equal to 1, right? Then D2 is equal to Q1 XOR with Q3, so Q1 XOR with Q3, that is 0 0, and that is 0, and that means Q2 in next cycle will be 0, and D3 is equal to Q2, D3 is equal to Q2, that means Q3 will be simply equal to Q2 of the previous cycle, right? Now in the first clock cycle, Sn now is 0 0, and we have these contents. Now second clock cycle, and we have this 0 from this Sn, and we know that D1 of the previous clock cycle was equal to Sn XOR with Q3, that is 0 XOR with 0, that was 0, so Q1 is 0, and D2 Q2 will be equal to D2, so and Q2 of the previous D2 of the previous cycle was equal to Q1 XOR with Q3, that is 1 XOR with 0 is 1, and here we'll have simply Q2, because D3 is equal to Q2, D3 is equal to Q2, and Qn plus 1 is equal to Dn. So that means Q3 of the next cycle will be equal to D2 will be equal to D3, and D3 is equal to Q2. Similarly, we are following this trend, and finally after the 10th clock cycle we are having the remainder bits at 0 1 1. So 0 1 1 need to be appended to the original input stream. This was also an interesting question. So here we have these two shift registers where their initial contents were 0 0 0 1 0 0 1 and 1 0 0 1 0 0 0 1, and the full adder sum output was connected to the serial input of the register A. The carry output was connected to the T flip-flop. The carry input was connected to the output of the T flip-flop, and BI was connected to the serial output of the B register. At the state initially AI this is AI, and this is BI. AI was 1 and BI was 1, and my Q was 0 as given in the question. Then that implies my S will be equal to 1 plus 1 is 0 1, that is SI equal to 1 and CI equal to 1. That means SI is equal to 0 and CI equal to 1. and this Ci is going to the input to the T flip-flop. That means as Ci is equal to 1, the output will toggle, so Q will become 0, that was 0 will become 1, and now Ai are 0 and 0, so Ai is equal to 0, Bi is equal to 0, Ci minus 1 is equal to 1, so Si will be equal to 1 and Ci will be equal to 0, right? As Ci is equal to 0, Si equal to 1, that one will be here, so that means contents will be updated here. So this 0 comes from here, this one comes here, this one comes here. That means these are serially going in, these SIs are serially going into the A register. And now we have this clock cycle 3, so Ci was 0, so Q will remain as 1, Q will remain as 1, and my inputs are 0, 0, so the sum will be equal to Q is equal to 1, that means Ci is equal to 1, so sum will be equal to 1 and Ci will again be equal to 0. Again my Q will be equal to 1, my Ai and Bi are 1, 0, so my sum will be equal to 1 plus 1, 1 plus 0 plus 1, so A is equal to 1, B is equal to 0 and C is equal to 1, so that means sum is equal to 0 and carry is equal to 1, and this 0 will go here to the next cycle. Now for the fourth clock cycle, Ci is equal to 1, that means output will toggle, Q will be equal to 0, my Ai and Bi are 0, 1, so my Si will be equal to 1 and Ci will be equal to 0. Ci equal to 0 means Q equal to 0, my Ai and Bi are equal to 0, 0, my Ai and Bi are equal to 0, 0, my sum will be equal to 0, my Ci will be equal to 0, and this will come, and this thing will come here, this will come here, so 0, 0, Q will remain as 0, my Ai and Bi are equal to 0, 0, so it will be 0, 0, 0, so sum will be equal to 0, carry will be equal to 0, so this will go here, and finally my inputs are 0 and 1, and my Ci is also 0, so output will be 0, so Si will be 1 and this will be 0. Now register B doesn't have any content, so the output will stop, and after 8 clock cycles this 1 will come here, and my contents of the register will be 1 0 0 1 0 1 1 0. So option B was the correct answer. So I think that was all. Let me just wait for a couple of minutes, maybe someone might join, and if nobody joins, we can close the session. We will meet at 3 p.m. on next Sunday, where we will discuss the contents related to, where we will discuss the problems related to week 9 lectures. Week 9 will have counters related to problems, and we will extensively look at them. Let me just wait for a couple of minutes, and then we can end the session. So let's just end today's session. So in case someone will have any doubts after watching the recordings related to this live session, he or she can discuss it with me next time when we'll be having week 9 tutorial. So thank you guys for joining, and thank you guys for watching this video. So we'll meet next Sunday at 3 p.m. discussing week 9 tutorial. Thank you so much for joining. Bye.